Okay, I would like to thank the organizers and especially Ronan for pushing very hard the network activity and for making it possible that this Balkan workshop is my talk is cubic algebras and generalized statistics, and it is based on a common word cubic algebras. There was a renewal interest recently in cubic algebras, and it is in relation with string theory, namely the variables of the matrix model of string theory satisfying equations of motions that have the form of the Arrhenius equations. These equations of motions were shown explicitly yesterday in the Balkan's talk. So the notion Young-Mills algebra was introduced, and it is the associated algebra that is behind the Young-Mills equations in D+1 dimensional, so the Euclidean space with metric J-member. I have written here the following Young-Mills equations, where the variable that satisfies these equations is three-dimensional. It's very intuitive. It can be also variable in the matrix model. This is an associative algebra, and it is a universally distributed algebra generated by D+1 generators. If one thinks just these generators as abstract generators, obeying the D+1 cubic relation. So now this algebra means that any solution of the Young-Mills equation carries a representation of the cubic algebra, the Young-Mills algebra. But this is an open field. So this cubic algebra has now been investigated as an abstract algebra. Almost nothing is known. The representations are not known. And so, if one studies and obtains a complete description of the representation of this algebra, this will enrich the variety of solutions of Young-Mills equations, and even in relation to string theory, people mention that this may be useful in solving a problem, H, whose strings corresponds to string theory. So this is, so to say, an introduction of cubic algebras, and there is, however, a very good example of application of cubic algebra to physics, and this is parastatistics. Why I make the connection? Because this algebra has a quotient, and the quotient is the para-Fermi algebra, the homogeneous part of the para-Fermi algebra. The relation between gauge theory and parastatistics has been known from the very beginning. Parastatistics was introduced in 1953 as a generalized quantization method by him. And it was introduced as an alternative to the conventional Fermi-Posé statistics in quantum theory. Very soon after the introduction of parastatistics, there was a paper by Greenberg on the field theoretical method with 3 degrees of freedom with parastatistics. And in this paper, in fact, the author introduced color. He introduced the SU3 symmetry without knowing this. So some years later, in the 90s, there was a rigorous paper by Doppler and Roberts, who proved rigorously this relation between parastatistics and gauge symmetry. With the invention of quantum groups, there was interest in deformation of parastatistics algebras, and I'm going to talk about deformation of parastatistic algebras, a definition of deformed parastatistics in a consistent way as a Hopf algebra and with a non-commutative product, and also the possibility from this non-commutative product to define generalized analog of the Boole representation for parastatistics. So as I said, parastatistics, I will just mention for completeness and to make things more transparent for one to follow. And because when one is doing deformations, one usually follows the analogy with conventional parties. So here is a definition of green parastatistics. It is, so these are two families of algebra, Parabolic algebra and Parabolic algebra of operators, Parabolic operators, that satisfy three linear exchange relations. So they are inhomogeneous and homogeneous. So here the indices minus plus, minus is commutative, plus is anti-commutative, and minus is for the para-family case, plus is for the para-Bouvet case. And of course, this algebra can be written in a supersymmetric way if because of these commutators and anti-commutators, one can write it in a compact way, introducing grading of the operators. So the para-Fermi operators are even, the Parabolic operators are odd, and what is important also is that this algebra admits linear evolution. This is conjugation. So in fact, these operators are creation and manipulation operators, and one, of course, sees that this the commutated between A plus and A minus G closes the sub-algebra, which is the GLN sub-algebra. What is important for this, for the Parabolic algebra, is that they are isomorphic. So the Parabolic algebra is isomorphic to the universal enveloping algebra of the orthogonal algebra SO2n+1. And the Parabolic algebra is isomorphic to the universal enveloping algebra of the orthosymplectic algebra OSP1 to n. So this is the meaning of these three linear relations, and thus these relations provide an alternative presentation, alternative relations for the algebras SO2 n+1 and OSP1 to n. So it is also important to say that the representation of these cubic relations, of these cubic algebras, is characterized by an integer p. And the meaning of this integer for parabosons, it is the maximum number of particles that sits in an antisymmetric representation, in an antisymmetric state, so corresponding to Young block with up to p rows. And for Parabolic, it is the maximum number of particles that sit in a symmetric state corresponding to young block with at most P columns. Now the idea of deforming our statistics now is to quantize this isomorphism. So to deform in such a way the paraphermi and the parapositive relations that paraphermi is isomorphic to deformation of this universal algebra and parapositive isomorphic to deformations of this universal algebra. So this is what is written here. This is the guiding principle in obtaining the formations of our statistics. Now, it is one important thing which maybe is not very known, that these universal enveloping algebras have the same Cartan matrix. I will it here explicitly. So this is one and the same matrix for both cases. And so we can write the defining relations of these universal enveloping algebras in a compact form. So, so the deformation of these universal enveloping algebras is now English Fourier basis, so we shall use it. And we, of course, we have the Cartan generators and the lead operators corresponding to the simple roots with the corresponding grading. Of course, all the generators of the universal enveloping algebra here are even, and here we have one of the generators. Now here is here are the relations that define this universal enveloping algebra. In order to quantize and to show isomorphism of parastatistics to these algebras, we have to write these algebras in the Cartan-Weil basis, the analog of the Cartan-Weil basis, and this is done by changing, and this is done by change of basis by using the subset. Okay, this is jargon short roots by changing from the simple root to a system of orthonormal roots. This is the guiding, the essential point in proving the isomorphism. So the change of base on the Cartan algebra. Now this is here in the universal enveloping algebra in the basis show as it was shown simple roots, and here this is in the orthonormal corresponding to Cartan generators, and using as a basis the orthonormal set of roots. Of course, these operators commute by construction, and now we define the ladder operators. They are denoted small a, plus and minus, that correspond to the new set of roots. And they are defined by these multiple commutators. And we can use the inverse change and then express these generators corresponding to the simple roots in terms of the generators corresponding to the new basis, and then we have to insert this expression which gives the change of basis in the defining relations of the SO2n plus 1 and OSP1 to n deformed relations. relations express the adjoint action of the sub-algebra, the default GLN, the adjoint action on the ladder operators. The novelty are the novelty because, of course, we are not the first people who do the formation of parastatistics. There was some work with the beginning of quantum groups activity. There was some work done on the formation of parastatistics, and so the inhomogeneous relations are the same, but the inhomogeneous are the same. Other homogeneous relations have been obtained that did not allow to extend the algebraic isomorphism to a homomorphism. Now, the novelty, as I said, are these homogeneous relations, which are a bit strange because they are actually combinations of the deformed homogeneous classical homogeneous relations, but their form is crucial to extend the isomorphism to a homomorphism. So this these relations here form a complete set of the isomorphism. They define the formations of the parastatistics algebra, and now we have to prove also further that these relations define also a Hopf algebra. The universal enveloping algebra UQSO2 S.1 and default paraphrase are isomorphic as not only the algebras but as coalgebras too, so they are isomorphic as coalgebras, and the same for the para-Gaussian case. So here is also the same relations for the conjugate. So this is an algebra with involution. It follows from the involution of the universal enveloping algebras we started with, and I have here the corresponding involution. So once we obtain the one characterization, we can, by conjugation, follow the other set of relations. So the next problem is Hopf structure of parasitic algebras. This is not, it is known, but I have written for completeness the coproduct antipode counting for the quantum and universal enveloping algebras with two S.1 and so these are things that are in notebooks, of course, but now, so because we want to prove isomorphism is algebra, so we have algebra, so we have to define the corresponding Hopf structure. How this is done? So I want to show first a theorem, and it is the following: that the deformed Vrnjačka algebra and the deformed algebra is a common algebra and a Hopf algebra, respectively, when endowed with a coproduct defined on the generators in the following way. So here this is for the Cartan generators. Here is the product on the ladder operators, and you see that here it has some additional terms. So there is also a co-unit and an antipode, and of course there are many technical details in proving this theorem, but there is a very nice guiding principle And the guiding principle is seen very easily when one introduces the L functionals for the quantum universal enveloping algebras, this quantized universal enveloping algebras we started with. The L functionals, upper and lower triangle, of the formalism of the Shitikin Tartajan. And so on this conferences, these functionals satisfy the celebrated relations of this formalism, known, and the form of the L functionals is known for UQSO 2 n plus 1 and UQ was 1 to n. The matrix elements are these L functionals are expressed in terms of the corresponding generators. And now, since we changed the basis, now we express the matrix elements of these functionals in terms of the new generators. And they have a very nice form. So the L functionals for these two algebras are 2n plus 1 cross 2n plus 1 matrices. We have written here, we shall need only the left upper corner, which is n plus 1 times n plus 1 matrix. And we have written it, and you see that in terms of the power oscillators and in the small h generators, it has a very nice form. And now it is, and here the column in this upper part, this column, are exactly the generators. And it is also known, these L functions, they have a very nice property. They have a coproduct. I will write it now. I will show it now. Yes, so the L functionals have a coproduct, and from the coproduct, one can, just inserting the form of the matrix elements, one can obtain immediately the coproduct for the lead operators in the new basis. And also, it is not a problem to obtain also antipode and co-unit for the deformed parastatistics cell. So indeed, this is we have proven that the deformed parastatistics is the two deformed parastatistics algebras are Hopf algebras isomorphic to the quantized universal developing algebras, the corresponding one in the two cases. And now this non-commutative coproduct can be used to define the generalized version of the green representation. And again, I will remind here green parastatistics, the classical one, and green ansatz is a representation of this cubic algebra is obtained in representing the para operator as sum, the para operator of order of arbitrary integer of order p, as the sum of p term corresponding to the lowest representation, P equal 1. So P equal 1 are, in fact, usually the conventional Fermi oscillators, and in the case of the deformed case, these are the parallel. This is the Manin plane, and here is the deformed. Here are the deformed Vrnjačka oscillators. This is the simplest representation of the deformed parastatistics. Okay, so and it is important for this Green and Zap representation that the inner components obey anomalous commutation relations. So inner components with one and the same label obey the same quadratic relations, Fermi for parafermi and Bose for parabose, while inner components with different labels obey the opposite commutation relations. So therefore, they are said anomalous. And this is written here, as you see. Now these, the labels in bracket are the labels for the inner components. And now we want to generalize this Green and Zap. And how? By using the coproduct. Because if we take a para operator of P equal 1 and define the coproduct, then each part of the coproduct with a different space has P equal 1, but as a whole we increase the and so by iterating the non-commutative coproduct, we can define the inner components of the deformed parastatistics. And okay, so here is how we iterate the coproduct. So I'm sorry for this mistake. So 0, this is of course convention, and this is iteration, but this is the convention. So 0 is equal to the co-unit, label 1 is identity, and delta 2 is the usual coproduct. And by iterating this coproduct, we we define a representation of the deformed parastatistics. So the green components are defined in the following way. And now defining explicitly the green components by using the iterative coproduct, the only thing that remains is to calculate the commutation relations between the different components. It is a very tedious and very long calculation, and I will show the results of this calculation. So we have the same principal rule. So equal components obey the same type of deformed relations. Fermi for parafermi and Bose for parabose, and different components obey the opposite deformed relations. But they are very complicated because sometimes they admit additional terms. Okay, it is a complicated quadratic algebra of anomalous deformed commutation relations, but it defines in a consistent way a representation of the deformed parastatistics. we have defined deformation in classical green power statistics, and we argue that this is the exact quantum analog of the classical green power statistics. Thank you.
Are there any questions or comments?
I have a question. I don't recall now how it's, but can you make such a deformation to lead to some physical implication? For instance, can you describe small violations of Pauli principle, things like that? I remember that in principle you can do it, but only with large violations of Pauli principle.
We haven't talked about
So that would be very interesting.
yes, sure. This is okay. We are happy now to have a consistent
No,
definition.
it's
So,
no.
but okay, of course.
Are there any other questions?
In connection with the quantum universal enveloping algebra, OQ
Yes.
2n plus 1.
Yes.
There exists one other cube deformed universal enveloping algebra corresponding to the same classical object, which is defined not by means of cardinal elements and simple rules, but in terms of just cubic relations, just linear relations. But the other thing is that there are problems with common application structure.
Yes.
And it seems to me that it's essential.
Yes, this is essential. So we have defined in such a way that it is in the deformation. It's in the
Are there any questions? If there is no, let's take the speaker.